Okay, so we are very happy to have Peter, and he will tell us about the Large expansion and string theory out of equilibrium. Please start.
Well, thank you very much for the invitation. It's a big pleasure to be back in Berkeley, where I'm normally. So it's great to give a talk. It's actually my second talk in this Berkeley seminar this year. I gave one on our work on Ricci flows in the string math seminar about a month ago. So this will be on the other topic that we have been working on over the past year and a half, and are continuing to work on. Oops. I think my screen is refusing to move. Okay, now it's active. Looked for a while that it was frozen, the ability to move pages. Hopefully it's gonna stay stable. Okay, so this is based on 3 papers that we published with my student Chris last year. And also we continue working on this with both Chris and my new student Andres. So this has been a very exciting time for us. We finally started connecting 2 different things, and that's the idea of non-equilibrium physics and string perturbation theory. This is something that has puzzled me for maybe decades. Why is string theory so great at describing things that are very static and stable and eternal, and perhaps not so great at things that evolve rapidly with time and are away from equilibrium? Of course, historically, the reason why string theory is so great at describing static, stable, eternal configurations, especially those that are highly supersymmetric, the reason for that is rooted in the historical evolution of string theory. As we all know, in the 60s, string theory originated very intimately from the S-matrix program, pioneered primarily here in Berkeley. And as a result, it developed into a beautiful candidate for unifying quantum mechanics, fundamental particle physics, and eventually quantum gravity. So today, it's our most favorite theory of quantum gravity, but the origin in the S-matrix logistics are still seen here and there in string theory. And I think in particular, even though string theory has been so successful in helping our friends in other neighboring areas of physics, including particle phenomenology, to some degree condensed matter physics with ADS-CMT correspondence and other aspects, even K-theory influences, and to a certain extent cosmology, I'm still somewhat frustrated by seeing how difficult it is to actually make significant progress in understanding quantum gravity out of equilibrium using string theory, in particular in cosmological settings. If you compare how great string theory is in describing highly supersymmetric configurations, we have so much control, we have solved so many brain-like configurations, used it to engineer all kinds of exotic, very controllable field theories and other limits. On the other hand, if you look at how difficult it is to get just, for example, the simplest de Sitter spacetime out of string theory, you have to jump through all kinds of hoops and attach all kinds of bells and whistles to constructions. It doesn't seem particularly natural in string theory. And my question has been for decades now, is this a fundamental limitation of string theory as we understand it? Or is it possible that perhaps we haven't understood string theory from the proper angle yet to see how it can help revolutionize perhaps cosmology and other non-equilibrium phenomena, including quantum gravity? So my prejudice here would be to assume that somehow we still haven't seen all of string theory, but how do we start seeing what we are missing? What are the missing ingredients? What is the proverbial foot in the door to see how to open up some new vistas in string theory? So again, since our plan is to take systems away from equilibrium, we can ask ourselves, this is still part of the introduction, we can ask ourselves, in other areas of physics, including quantum field theory, condensed matter physics, many-body physics, is it known how to take systems away from equilibrium, or are those fields also similarly attached to the idea of the S-matrix? And then the answer there is, of course, well known. It has been well known since at least the early 60s. And the answer is that these other fields of physics are perfectly capable of taking systems away from equilibrium, at least in principle, by invoking the full formalism of quantum mechanics. For some strange historical reasons, this full formalism of quantum mechanics in this context is referred to often as the so-called Schwinger-Keldysh formalism. To me, that's a slight misnomer. I would just call it quantum mechanics without assumptions, without making assumptions about the existence of the static, stable, eternal vacuum, which are almost always made in textbooks on high-energy quantum field theory, where you start with the standard formalism of relativistic quantum field theory in Minkowski spacetime, and there the assumption of the static, stable, eternal vacuum is never even mentioned explicitly in most textbooks. Like Peskin-Schroeder would never talk about how that formalism is actually only kind of a half of the full formalism of quantum field theory. If you don't make the assumption that the vacuum, like in the S matrix setting, is eternal, static, and stable, if you don't make an assumption about knowing what happens at the end of the universe in the future, that you would be returning to the same asymptotic out state that you started with, without this assumption, the full mechanism of formulating quantum mechanics is still available. You don't have to modify any axioms or any assumptions. You just develop the full formalism of quantum field theory without the assumption of the static, stable ground state. And if you do that, you end up with a very logical and sensible picture. You start by assuming some kind of an initial state. This can be perhaps a non-interacting free vacuum. It could be some other complicated state. And then without making any assumptions about what the system ends up at the end of time, you just evolve. So you are interested, let's say, in correlation functions of Heisenberg picture operators in the theory located at various moments in time between T1 and Tn. So what you do, you use the system to evolve from the infinite past, from the initially prepared state. You evolve into the future until you are ahead of all the insertions of your interesting operators. And then without making any assumption about the state that you end up in, you just are forced to de-evolve back in time. So if you decode what this correlation function of Heisenberg picture operators means in either the interaction picture or even in the Schrödinger picture, what you start seeing are insertions of the evolution operator, which usually is called U. I call it sometimes S, because that's essentially what the S matrix operator is. So in textbooks, you often see this called capital U. Regardless of the notation, this is a time-ordered product of the exponential, or time-ordered version of the exponential of whatever interaction part of the Hamiltonian, roughly speaking, you have. Notice that in the full correlation function, if we do not relate the out state vacuum to the in state, we are still returning back to the in state, and the mechanism how we evolve there automatically puts in an insertion of the inverse evolution operator here. So that just represents the fact that you have evolved on a doubled time contour. You have followed the evolution into the future while inserting all these operator insertions, and then you have turned around and without any additional insertions of anything, you've de-evolved the system to the infinite past again. So that's the full formalism of quantum mechanics. It's nothing revolutionary. It's just that it's often not taught in introductory courses on high energy quantum field theory. So if we represent this in a graphical language, we might think of the system as starting at some point in time t0, and then the time evolution is represented here by, let's see, is represented by a doubled time contour. You first evolve into some time in the, well, perhaps infinite future, or some finite time in the future, which is later than any other interesting physics that you are studying in the process. So this part of the contour I'll refer to as C+, and then after turning around, you evolve backwards along the backward side of the so-called Schwinger-Keldysh time contour. This is just a simple graphical representation of what we did with the correlation functions on the previous transparency. So the moment in time where we turn around is some instant, which I'll refer to as T wedge. The notation is simply to indicate that this is kind of the wedge part of where the two branches of the contour meet. So that explains the notation. So the contour consists of two one-dimensional segments, C plus, C minus, and they're connected in a one point, which you can think of either as infinite future or far away into the future, so that you don't have to worry about how far into the future it is. On the other hand, I should also mention that in cosmology, people are also using this full formalism in effective field theory approaches to inflation. This was an approach primarily pioneered in the early 2000s by none other but Steven Weinberg, who formulated the proper way of understanding correlation functions in evolving cosmologies using a version of the Schwinger-Keldysh formalism, which is adapted better to cosmology. For such questions, the time t wedge is not in the infinite future. Instead, you interpret the same mathematics by saying that t wedge is our present. This is when we are observing correlation functions in the sky. And we are not making assumptions about the future evolution. We are simply making an assumption about the initial state, evolving the system from the infinite past or some finite controllable past to the present, then inserting interesting correlation functions here at t wedge instant, and then evolving back into the past. So this is, in Weinberg's case, called the in-in formalism. That's yet another common terminology for the same structure. So this is all just fundamental quantum mechanics without making any assumptions. And I like that because that makes the question even more pressing. How can we reconcile this with fundamental principles of string theory? Is string theory capable of seeing this structure, or is string theory inherently rooted only in the S-matrix formalism without the possibility of relaxing the assumption of the infinite static vacuum? So when we put field theories on such a Schwinger-Keldysh time contour, something well understood happens. You can either keep track of the values of a field phi, let's say for simplicity we consider a single scalar field phi, and I can certainly calculate correlation functions of 2 copies of phi on the forward part of the contour, or I can calculate correlation functions such as a propagator, in this case, between 1 copy of phi on the forward branch and then another copy of phi on the backward branch. This, of course, leads to the fact that instead of just the Feynman causal propagators, we'll have to introduce all 4 possible different propagators into the game. There will be Feynman propagators, like the light green line here. There will be anti-Feynman propagators that represent correlation functions of fields on the backward part of the contour. And there will be plus-minus propagators and minus-plus propagators that take us from one branch of the time contour to the other. So this is the full picture. All 4 different types of propagators make an appearance simply because we had that factor. If you remember this formula here, we have the factor of S inverse in front of the time ordering. So there will be certainly correlation functions of all kinds of time order products of fields showing up in the perturbation expansion. That's why we need all 4 propagators. Nobody is surprised by this anymore. A while back, this was still new to high energy physics, but I think we are now getting used to it under the influence of the evolution of our field in the past 10 years. So nobody is surprised by this. And the question is, how do we put string theory instead of particles, word lines of particles and propagators representing 2-point functions of scalar fields? How do we put string perturbation theory on this Schwinger-Keldysh time contour? So what you expect naively is perhaps that the string evolution, when you evolve a string state in real time in Minkowski signature into the future and perhaps try to land on the other side of the Schwinger-Keldysh time contour, perhaps this will lead to worldsheets with cuts. There will be a forward part of the worldsheet, which will be a 2-dimensional Minkowski signature geometry, at least naively in some classical intuitive naive picture. And then perhaps there is a boundary on the worldsheet, and what's on the other side of the boundary might be naively perhaps residing on the backward part of the contour.
Petr?
The reason why we published these papers is that this is precisely not how it works. Yes.
Sorry. Yeah, just before you get into the string theory part, can you illustrate a little more? Like if I'm interested in cosmology, for example, and I'm an experimentalist who measures the CMB right now,
right.
Then at least the most direct thing that I think I would be interested in, right, would be somehow the amplitude for different things to observe various different things in the CMB.
Right. So
now, which would sort of involve a forward evolution, but not so obviously a backward one. Could
you have to land somewhere, right? You have to close the correlation function somehow. So if you don't have the assumption that the universe will last forever and end up in a Minkowski state at the end of time evolution, then you don't have a good prescription how to close the correlation function. So the question is, mathematically, basically, the question is, what do we put on the left-hand side of this correlator? So let's say we are interested in cosmological correlations. So we will put all the observables here at the present, at the time t wedge. And we are agnostic about what happens in the future. We have evolved our system from the infinite past, or perhaps from the Big Bang, from some known state in our past. We have evolved it to the present. We insert these correlators, but in order to close the correlation function, we need to do something on the left side. And the most natural thing to calculate is the in-in correlation function. Since we don't have any information about the out state, you could try to postulate some kind of an analog of the S matrix for cosmology, but that's not a practical thing to compare to the experimental data. So instead, you de-evolve the system back, bring it back to the original known in state, and relate these correlation functions to your correlators in the cosmological observables. So that's what Weinberg essentially proposed, and I believe the community has been following ever since those groundbreaking papers in the early 2000s. So now the question is, how do we formally put string perturbation theory, or does it even have such an extension to non-equilibrium? So this brings me to the title of the talk. So just going back to the title, this should be really read as two lines. I'm going to be talking about large N expansion and how it's related to string theory. This is a well-known story in the equilibrium case. So large N expansion famously gives rise to string theory. But now I'll be taking this relationship from line 1 and taking it out of equilibrium, asking the same questions, but relying on the fact that on the large N quantum mechanical side, we know precisely well, we know exactly how to take the system away from equilibrium, and perhaps that will give us some preliminary insight into what to expect on the string theory side. In my view, on the string side, we do not have enough power to actually guess what the correct structures should be from first principles, but we might use this large N duality to get some hints, and then we can look for specific realizations of the structure that the large N expansion predicts. So that's exactly my strategy, or our strategy. So again, this is another review of something really well known. So I apologize to those of you who are knowledgeable both about the Schwinger-Keldysh formalism and the structure of the large N expansion. Hopefully, this will still be useful for the rest of the talk. So we know very well that if we have any quantum mechanical system which has a matrix set of degrees of freedom, maybe SUN matrices adjoints of QCD, or maybe just a quantum mechanics, a matrix model. It could even be a non-relativistic system. It doesn't have to have any Minkowski Poincare invariance, doesn't have to be supersymmetric. And let's assume for simplicity that we are studying it in equilibrium. So we can take the partition function and following 't Hooft's famous guidance from the 70s, introduce a natural new expansion parameter, namely 1/n, and perform the large N expansion. And famously, if the system does contain matrix degrees of freedom, not just vectors or some other funny representations, then we end up predicting that the dual side of this theory, there is a duality. The dual description should be in terms of some more or less mysterious unknown string theory. But at least it shows us that there should be a string theory. We might have a hard time finding out how to describe that dual string theory from first principles on the worldsheet by formulating some dynamical principle out of the Polyakov action. But still, the partition function or any interesting correlation functions, they just reorganize themselves into this beautiful genus expansion, 1/n playing the role of the string coupling, and H being the genus of a surface. So there is a summation over geometries of surfaces, and all the interesting physics on the dual side is hiding in how these coefficients f sub h of each fixed genus depend on whatever couplings are also present, like the 't Hooft coupling of large NQCD, for example. So this is, of course, extremely well known. It was proposed in the 70s, as I pointed out, by Gerhard 't Hooft. And I believe in retrospect, this is a very big missed opportunity that the community had since the 70s. If people took this prediction more seriously, they could have arrived perhaps at the more precise formulation of ADS-CFT correspondence decades, or at least years before Maldacena, just by taking the correspondence more seriously and trying to fill in the details of the dictionary. So my question now is, aren't we as a community perhaps missing an equally important opportunity that we know now that this correspondence should hold even when we try to take the system away from equilibrium? So why don't we look at the larger expansion of the theory away from equilibrium on the Schwinger-Keldysh time contour and see what that predicts for the dual string theory? So perhaps we'll find some surprises that might guide us towards a better worldsheet description. This is what I'm after. So in case this is not clear, what I'm really interested in is the following question. Is there an extension of conventional string perturbation theory, which is perhaps your first definition of, at least historically, how you introduce string theory? Is there a natural extension of that formalism to non-equilibrium states? So just as a quick reminder how this matrix logic works, so we have a matrix, a set of degrees of freedom. It might depend on some additional indices or space-time dimensions, spatial dimensions, but I'm only going to pay attention to the dependence on time. I'll just factor out for simplicity some kind of a coupling constant overall, like in QCD, for example, we would have 1 over G Yang-Mills squared. And then formally, let's consider only single trace terms in the action. So I'll have trace. There's going to be a kinetic term. Perhaps there is a mass term, but I'll lump it together into the kinetic term. There is MQ plus M4, and so on. So simple Feynman rules follow from conventional arguments. They give us propagators, and because, of course, the degrees of freedom underlying the system are matrices, the propagators become ribbons, and ribbons are connected in vertices in such a way that the indices flow through in the natural sense. Everything is very intuitive, and you end up with these ribbon-like diagrams. And that's the sole reason why you can uniquely, with each ribbon diagram, associate a Riemann surface. If you had more primitive Feynman diagrams, which would not be made out of ribbons, you would not be simply able to associate a canonical surface with a given diagram. The structure of surfaces would not align naturally with the classification of all possible graphs. But here, because the graphs are all ribbons, we have this beautiful re-summation of the perturbation expansion by associating with each graph a surface, a Riemann surface of a certain genus first. And this, of course, works famously by fixing some particular combination of the original coupling and n, the large n parameter. And then the typical diagram will be proportional to n to the Euler number of some canonically defined associated surface sigma. So that's well known again. And just to show an example, combinatorially, we associate the Euler number with a surface. If I discretize the surface using vertices, propagators, and closed loops, I'll be denoting those by V, P, and L. V for vertices, P for propagators, L for loops. Geometrically, those are 0-dimensional, 1-dimensional, and 2-dimensional pieces of a simplicial decomposition of a surface. Then, of course, famously, this Euler number definition is well known and reproduces the genus H. So as an example, if you think about calculating the Euler number of this particular surface associated with this ribbon diagram, there is one crossing of these ribbons, one over the other in the middle. So this will give you a prediction that the surface is naturally associated with a torus. You can naturally draw it on a torus. And indeed, the Euler number calculated by this prescription gives you genus 1 as the result. So this is all extremely well known, and of course, is the ultimate reason why something like ADS-CFT correspondence ended up working some 20 years after the original 't Hooft prediction. So now we can try and mimic the same logic and push it away from equilibrium. So let's do it on the matrix side first. And again, it doesn't matter to me whether this is QCD, supersymmetric Yang-Mills, or just a matrix model or whatever else, as long as I have matrices in there. So I'll follow the strategy that I was about to explain when I was drawing these diagrams for particles or for fields. Instead of thinking about one field phi, taking two different values on the forward and the backward part of the contour, it is natural to reorganize that and say, I only have one time coordinate t, but each field phi will now be doubled. I'll call phi plus the value of the field on the forward branch at time t1, and then phi minus the value of the field on the backward branch. So instead of thinking about the doubling of the contour of time, you can think of this as keeping your conventional original time and just doubling the number of fields. So when that happens in our theory of matrices, we'll naturally end up doubling the matrix degrees of freedom. Let's call them again m plus m minus, as they depend on either the forward or the backward part of the time contour. And out of the machinery of quantum mechanics, you find out in the path integral representation of the system, the action will consist now naively of two pieces. You'll have the action in real time on the plus side of the contour, and then with an important minus side, because on the back side you're evolving backwards, you have minus times the action of the m minus degree of freedom. So this is going to be the typical structure of the action of such a matrix theory. So notice the novelty here will be the following. We'll have the same kinetic terms that we had for the equilibrium case, both in here for m plus and in here for m minus, perhaps with a relative minus sign, but the minus sign is not important. The important thing is that each end of a propagator will now be labeled by a sign, whether this end of the propagator is the m plus and this end is m plus, or they are m minus, and there's also a possibility of propagators that connect plus or minus and minus to plus. Those are the ones that would cross against the wedge time where the two contours meet. On the other hand, vertices will not be, unless we change the theory by hand, the vertices will not be located at the time t wedge. They will be either located inside this part of the action, they'll all depend on only m plus fields being attached, or they'll be completely inside this m minus part of the action, and therefore you can label each vertex by either a plus or a minus, and then the rule is that whenever each vertex has a plus or a minus, only the plus ends of propagators or the minus ends of propagators can be attached to them. So this is again very logical, very well under control, and we can draw Feynman diagrams. They'll again take the form of ribbon diagrams as before, but now these ribbon diagrams will carry a refined structure.
So,
yes?
Don't you have mixed vertices? I mean, mixed in plus and minus?
Not in this formulation. If I try to modify to cosmology, then I might modify the action accordingly. But this is the case which corresponds to T wedge being after everything interesting happened in some remote future. And then you just get this formal sum of, or rather the difference between the m plus and m minus part of the action as far as the interactions are concerned. But again, this is up to you. This is one of the knobs you can turn. You can try and ask what happens if I, in addition, also add some interactions at the T wedge moment in time. Nobody stops you from adding terms in the Hamiltonian that have that particular shape, and you would end up with something which is more closely related to Weinberg's cosmological setup.
So the difference from propagator and the vertices is whether you have a derivative term in action. Is that true?
No, it's more subtle than that. It's basically a question of boundary conditions.
Yeah.
For propagators, you really end up having the fact that the plus and the minus branch of the contour are not disconnected. They meet at some point in the future. That gives you a non-trivial plus minus and minus plus propagators. And on the other side, the vertices can be turned off completely, so you can have no self-interaction in that remote future. But if you want to, you can bring in interactions and ask more sophisticated questions. What happens in the presence of those interactions? But that's outside of what I'm going to be doing today. Just for simplicity, let's consider the case where T wedge is really in the remote future. After everything of interest has happened. That's how it would be applied in condensed matter physics.
Okay, thank you.
Okay, so now the question is, now that we have these ribbon diagrams and we have three different types of propagators, the fourth one is just a reversal of the third one. So there are really three independent ones labeled just by the three different combinations of signs at the ends. And then vertices are labeled by either plus or minus. We can start asking, what is this additional refined structure that we are getting out of the canonically associated two-dimensional surfaces in the large N expansion of this theory? So perhaps the first naive guess would be to say that just like in the case of, oh, my cat is unhappy about something. He doesn't like when I introduce cuts in propagators of ribbon diagrams. So if he meows more, we will have to address it. But anyway, I hope he's not going to interfere with the talk too much. So your naive guess might be that just like in the case of point-like particles, the propagator that connects the plus and the minus side of the Schwinger-Keldysh contour can be represented by a cut propagator. This is not a coincidence. There is actually a very, very close connection between the Schwinger-Keldysh formalism on one hand, which is fully non-equilibrium and all that stuff, and the Katkowski rules of unitarity in conventional relativistic quantum field theory on the other. The connection is that if you take the full Schwinger-Keldysh representation of quantum mechanics and try to take the equilibrium zero temperature limit, you can do it in two different ways. You can do it in one way where you allow all the interesting correlation functions to be inserted only on the forward branch. And in that case, it's very easy to show that in the zero temperature equilibrium limit, the other side of the contour just simply decouples and disappears. Or you can take a more sophisticated limit where you allow yourself to make insertions of operators on both sides of the contour and still take the zero temperature equilibrium limit. And it's somewhat less known, but it's a true statement that in that case, what you reproduce are simply the Katkowski rules of unitarity for calculating the S matrix properties in equilibrium at zero temperature. In other words, in the Katkowski diagrams, we have the sunny side of Feynman diagrams and the shady side separated by cuts, and the propagators that connect vertices on the two sides of the cut are the so-called plus minus or minus plus propagators. They're represented by on-shell delta functions. That's exactly what you get from Schwinger-Keldysh in the zero temperature equilibrium limit. So this might be your naive guess that first, when you try to reconstruct Riemann surfaces out of these different kinds of non-equilibrium propagators, you might end up with worldsheets with cuts.
Petr?
Yes.
Can I ask you like how to understand that intuitively? Because intuitively, I think that you have a two class of vertices, plus and minus, and you can connect any combination, plus, minus, plus, minus, because you have our propagator.
Yeah.
So if you take a limit of the dense diagram, then it looks like kind of like grayish. Let's call plus is a black, and then white is right, minus is a white.
This is an excellent question. That would be a question of what happens when you try to take some kind of a double scaling limit, where you really produce the full local dynamics on the worldsheet out of having very dense diagrams.
Yeah.
That's again beyond the scope of today's talk, but it's an excellent question. I'll try to guide towards answers towards the end of this, but again, we'll be mostly spending time on finite diagrams with a finite number of vertices, not taking the dense limit. But the dense limit would be a very fascinating next step to take. Mm-hmm. So let's test this idea that perhaps worldsheets are now split into the plus parts and minus parts separated by boundaries. For some simple diagrams, that works. So if I draw this particular ribbon diagram with just one plus vertex, one minus vertex, indeed, there are 4 G plus minus propagators, and I can naively think of the surface as being a sphere that's split into two halves separated by a boundary. But for some more complicated diagrams, that doesn't work because there are ambiguities which need to be resolved. So this is an example of such a diagram. It has 1 plus vertex on the left side and 3 minus vertices. And it's also a non-planar diagram. So there's going to be 1 plus minus propagator here, 1 plus minus propagator here, 1 plus minus propagator here, and then a bunch of minus minus propagators. When you try to follow the prescription that I gave, that each plus minus propagator should be represented by this blue line that cuts across the diagram, you find out when I redraw this diagram in an equivalent way, there is a plaquette. If you think about the topology of this diagram, there's a plaquette here which has 8 edges, and it's being cut 6 times. So there's certainly an ambiguous way how these naive cuts across each individual propagator should be connected to each other. So the cut across the propagator does not determine how the cut is extended through the plaquette. There is an ambiguity which you somehow need to address. So we could say, oh, fine, there is an ambiguity, so we'll end up summing over all these complicated ambiguities. That's not what comes out as the best scenario. We can do better than that. We can do the following. We can make this connection of all the different cuts across propagators inside the plaquette be unique by connecting all the individual cuts across all the plus minus propagators into a vertex in the middle. So that's my prescription for how to resolve the ambiguity. Instead of having just boundaries representing how the plus and minus part of the worldsheet will be connected to each other, I'll have boundaries with vertices. So I'll have graphs representing cuts, and that is not very pleasing yet either. So far we have made the ambiguities go away by replacing them with unique structures, but the unique structures are very complicated. They represent these blue lines connected with vertices with an arbitrary number of, well, arbitrary even number of lines being connected. And that's not very pleasing. I think it's much more pleasing to observe that you can slightly widen each of these complicated graphs and produce a two-dimensional surface with a smooth boundary associated with each such cut graph. So this is indeed the topologically universal construction that gives you a unique decomposition of every associated surface sigma. And it suggests something that to us at least was surprising. We were fully expecting that the worldsheet will decompose into a part that's a two-dimensional surface with some arbitrary topology living on the plus side of the contour, and then a sigma minus part that again can be arbitrarily topologically complicated, have an arbitrary genus residing on the minus side of the contour. But what we are finding here is there is a third part of the topology, here illustrated in yellow, and that part is completely associated with the wedge region where the two parts of the time contour meet. And then you can try to make this into a conjecture that there would be arbitrary topologies of this triple decomposition of surfaces showing up from classifying all possible ribbon diagrams. So you can ask, what is the topology of this yellow region? Once I start collecting these different pieces of this yellow surface, as I map out the entire ribbon diagram, I'll get some complicated topology. It's going to be a two-dimensional surface with these boundaries. Boundaries here are indicated in red, and they'll all be smooth circles. And this yellow region can be connected either to the plus side of the surface or the minus side, depending on what is the next bordering vertex after you've crossed into the white region here in the diagram. So again, long story short, we can provide explicit examples, and this is done in the first long paper of the sequence. The middle paper is a PRL which summarizes the results, so that perhaps is the first one you want to read if you want to just get an overview of the arguments. But then the first long paper provides this analysis on the plus and minus contour in detail, and we have shown that it's easy to construct ribbon diagrams where the wedge region, here indicated in yellow on that previous transparency, can be arbitrarily topologically complicated, meaning can have an arbitrary number of boundaries and an arbitrary intrinsic genus of its own, an arbitrary number of handles. So for example, we can show when you take these two half diagrams, one of them has only plus vertices, one of them only minus vertices. There are two possible ways of connecting these to form a full ribbon diagram. If you connect this in the naive way, you form a spherical geometry. But if you reorder the order in which the plus and minus half propagators are connected to each other, you actually form a geometry which looks like this. The sigma plus region is basically just a disk that contains all the plus propagators, and its boundary would be here. The minus part of the worldsheet is just a disk that borders these the minus vertices. And the rest of the surface is the sigma wedge region, and you can calculate in terms of n, this integer n, that tells me how many vertices I'm using. If I glue them in that opposite order as I was suggesting, there is a relation between n and the number of handles inside sigma wedge. So this is a lot of fun to trace the topology of all these surfaces and start forming proofs that any arbitrarily complicated topology can appear from a ribbon diagram. When I say arbitrary, what I mean by that is the following. We characterize it by the so-called measure once, cut twice principle, that if there is a cut in your propagator, in other words, if there is a sigma plus region and a sigma minus region, you might choose to cut where the sigma plus region ends. So that gives you a collection of S1 boundaries, but you must then cut a second time and tell me how many boundary components connect sigma wedge and sigma minus, and the topology inside between these two cuts can be arbitrarily complicated. So there is a strange but fascinating connection. This is a completely mathematical arbitrary detour for one transparency. I hope you allow me this, even though this is perhaps not as mathematical an audience. It's still fascinating to me that this sigma wedge region, which again, we can show can be arbitrarily complicated in the sense of having arbitrary number h of handles inside and arbitrary number n plus of boundaries connecting to sigma plus, and arbitrary number n minus of boundaries connecting to sigma minus. This region, if I try to look at all the ribbon diagrams that span these types of sigma wedge regions, there is a bizarre but mathematically provable one-to-one correspondence with a famous structure in purely abstract mathematics. Grothendieck, I think in the 80s, proposed the so-called descent d'enfant, which is a certain class of formally defined diagrams which happen to be bipartite in terms of the decomposition of the vertices. So vertices can be labeled by black and white, and only lines that connect black to white are allowed. And then you want to be also able to associate a surface on which this diagram is supposed to be drawn. So that's a rough definition of Grothendieck's descent d'enfant. You can classify them in principle, and they are related to such bizarre mathematical fancy terms such as the absolute Galois group and its various faithful representations on various categories. So there are long mathematical textbooks written on these descent d'enfant, and apparently just about any branch of mathematics that's of any interest is connected to this in one way or another. So I don't really know much about this, but if you draw this type of descent d'enfant as an example, you can uniquely associate a sigma wedge. So there is a one-to-one correspondence. This is our theorem, which we have proven without knowing what this might be good for. If you erase from any ribbon diagram all the information about the sigma plus and sigma minus part, oh, this is a typo, that's unfortunate. So if I erase all the information about the sigma plus part of the worldsheet and the sigma minus part of the worldsheet, keeping only the information about the sigma wedge region, there is a one-to-one isomorphism between such reduced ribbon diagrams and the descent d'enfant structure of Grothendieck's. Basically, the idea is that if the ribbon diagram, when truncated to the sigma wedge region, extends into the plus region, you label it with a black dot. If it extends into the minus region, you label it by a white dot, and then you prove that the universality classes are in one-to-one correspondence. I have no idea what this is useful for, if anything, but it is fascinating to me to see that the sigma wedge region, which is the novelty of this non-equilibrium expansion in string perturbation theory, is so deeply related to such a profound mathematical structure. So I'm hoping that somebody at some point will tell me why this connection exists between non-equilibrium string worldsheets and this Grothendieck structure. But back to the physics lessons that we can extract from this, we can now prove one of our main observations, namely the sum over worldsheet topologies, is now refined when we take the matrix system out of equilibrium. Instead of a sum over just a single genus H and a single topology of a Riemann surface, we are summing over all triple decompositions. And again, we have a proof in paper 1 that all possible quantum numbers show up, all possible genus numbers and numbers of boundaries do correspond to some non-trivial examples of ribbon diagrams. So a typical surface that would correspond or would contribute to the expansion would be labeled by all these separate invariants. The number of handles on the plus side of the part of the worldsheet, number of handles here, number of handles of the crossover from plus to minus, and the number of boundaries that connect the sigma wedge to the two sides. And again, as you see in this example, the number of boundaries here on the left doesn't have to be equal to the number of boundaries on the right. And in principle, all these things do appear in the Feynman diagram expansion of the non-equilibrium matrix theory in the large N duality. So this is a preliminary conclusion, but you can now say we have shown that there is enough topological structure to suggest that perhaps there should be a refinement on the string side. These are now speculations. How do we start developing some string perturbation theory? Our prediction is that string perturbation theory for strings out of equilibrium should really reorganize itself into this triple sum over these topological invariants of surfaces with the triple decomposition. That already is surprising to us. And it will be fascinating. This is what we are actually working on as we speak for the past many months, trying to see if this can be substantiated by specific string theory examples, either in critical superstring theory or in some matrix models or whatever examples one can think of. You should be finding this triple decomposition, and in particular, the dynamics, the worldsheet dynamics of this wedge region, sigma wedge, should be very interesting. So now that we see this triple decomposition structure, there is certainly enough topological structure to propose that it should be possible to weigh the genus of the plus part, genus of the minus part, and the genus of the wedge part of the worldsheet by a different string coupling constant. So far, they're all related to 1 over n, but we know very well that in conventional critical string theory in equilibrium, it is very easy to find configurations where the string coupling is not frozen to be just 1 over n once and for all, but it can vary with the space-time geometry, the linear dilaton diagram being the simplest example, perhaps. So it's not inconceivable to imagine that you might dial different values of the string coupling on the plus side of the contour, different values of the string coupling on the minus side, and a different value of the string coupling at the wedge part of the triple decomposition of the Schwinger-Keldysh contour and the worldsheets. So there should be an appropriate weighing of the surface contributions in string perturbation theory that sees this more refined structure. So this is one of my main points. I also want to highlight that we have extended this analysis to several different directions. One natural generalization that one might be interested in is to ask what happens when I want to be in equilibrium at finite temperature. And in that case, you can famously represent the temperature dependence of the Boltzmann factor in the partition function by extending the contour into an imaginary direction by some imaginary amount I beta. And therefore, instead of having just the forward and backward real-time contour, you can also have an imaginary segment. If you collapse C plus and C minus such that you're only left with the Euclidean signature contour, this is of course the famous Matsubara type representation of ensembles at finite temperature. So the fact that you can represent this by periodic Euclidean signature time. But by doing that, you prevent yourself from being able to insert interesting correlation functions or observables along this contour. This more complicated triple contour gives you more access to non-equilibrium phenomena on top of the finite temperature ensemble. So we can just as well keep all three parts of the contour and repeat the decomposition of surfaces. So we did that, and I'll spare you the details. They can be found in paper 1 of that sequence. Now we'll have 3 different types of vertices. and correspondingly a 3x3 matrix of propagators. This is well studied, well understood in non-equilibrium many-body physics. There are textbooks written on this, except nobody has ever, to our knowledge, combined this with ribbon diagrams. So when you combine this with the ribbon diagrams, you will start seeing new features. For example, there will be a simple planar ribbon diagram, which has one plus vertex, one minus vertex, and one vertex located on this Euclidean segment, which is often referred to as the Matsubara segment by the non-equilibrium people. And then when you try to provide a decomposition of surfaces, you'll find that there is actually a 7-fold decomposition of sigma. Again, I will not spend much time trying to discuss this in detail. I'll refer you to paper 1 if you want to see the details, or I'm always happy to talk about it privately afterwards. So extensions naturally exist, and it's a 7-fold decomposition. In the second long paper, which was paper 3 on my original list of references, we extended this structure into another very important direction, which is very, very popular in the Schwinger-Keldysh literature. It's a very simple, deceptively simple change of variables that people find extremely useful. This change of variables is a simple combination. For example, for the matrix degree of freedom M, you take the superposition of the forward and the backward value, call it M classical for short. It's a slightly misplaced terminology, but it makes some logical sense. And then you take the difference between the forward and the backward value of the field and call that M quantum. The reason for the terminology is essentially that there is an approximation where you neglect higher order terms in M quantum, and then you will prove that the remaining M classical in that semi-classical limit of M quantum being small actually satisfies the classical causal equations of motion. But regardless of where the notation came from, let's just accept this notation. Why is it useful? It's useful for 2 or 3 different reasons. One reason is, in our original plus-minus notation, we had 4 different propagators, and they satisfied one secret identity. When you sum all these 4 different propagators together, you get a 0. This is unfortunate in the sense that this means we had to draw many more diagrams than what was necessary, because we were not taking advantage of this secret identity. This was completely hidden, and in our original formulation of the plus-minus Feynman rules, this identity would require a summation over various types of diagrams to see the cancellations. So it leads to many, many more diagrams than you need. On the other hand, in these classical versus quantum variables, the propagators are automatically satisfying this identity, because as it turns out, the quantum part of the propagator is 0 identically. So you are left with only 3 remaining propagators. The 4th one being 0 identically, you can ignore it completely and end up with a simpler set of Feynman rules. The 3 propagators that you get in this case are the so-called Keldysh propagator. That's the most interesting one, because it carries the information about the state of the system. So if this is just a stable static vacuum, this Keldysh part of the propagator would become very trivial. And then the remaining 2 are the advanced and the retarded propagators, well known from conventional quantum field theory. So in case anybody was wondering, where do the advanced and retarded propagators naturally fit in, this is where they appear as the off-diagonal components in this classical to quantum versus quantum to classical propagation after the so-called Keldysh rotation of the variables has been performed. So this is the second very important reason why people prefer these Keldysh rotated variables. Namely, the advanced and retarded propagators here know only about the dynamics. The information about the initial state of the system is completely absent from GA and GR. Unlike here for the plus and minus propagators, not only do they satisfy this cryptic identity that you have to fish for in cancellations between different diagrams, but also all 4 of them, they have a mixture of information about the dynamics plus some information about the state. In the Keldysh variables, the dynamics is completely decoded here, and the state is completely encoded in the Keldysh part of the propagator. So it simplifies the physics. It separates dynamics from initial conditions in a beautiful way. So in order to get the Keldysh rotated diagrams, you have to introduce some traditional notation for the quantum versus classical parts of propagators. The typical notation is that classical ends are straight lines, quantum ends will denote by dotted lines, and now we're combining this with the ribbon features. So you end up with this fancy set of vertices and propagators. We found this notation cumbersome and developed our own simplified, we believe, or more intuitive notational language. And we call that signpost diagrams. Instead of having to keep track of these dotted versus undotted parts of propagators and how we connect to vertices, we indicate. So notice that because of the Keldysh-Schwinger structure of the action, all the vertices will always have an odd number of dotted lines attached, either 1, like here, or 3, or if you had higher order vertices, here you have 1, here you have 3. There's always an odd number of these dotted ends attached to vertices. So why not put a dot in the middle of the propagator and an arrow pointing away from the vertex in all the directions where there are these dotted ends of propagators. So the previous 4 vertices would be denoted by this arrow structure. And then you can reformulate conditions implied by causality by a very simple intuitive set of rules. Imagine that you are living on this ribbon diagram. You try to travel from one vertex to another vertex to maybe some distant side of the same diagram. You're supposed to follow the so-called allowed path rules. If you violate the rules, the diagram will be identically zero by causality. And the rules simply are, first of all, we observe that at each vertex, there is always at least one green arrow available to you. And the prescription simply is travel following the green arrows. Whenever you land at a new vertex, choose any other arrow and travel until you reach your destination. If in the process you form a closed loop, the diagram will vanish identically and you don't have to count it. So there are many simplifying features of this signpost notation. I'll spare you the details. This is all in paper 3 of that sequence, and leads to a different decomposition of the surfaces. Instead of a decomposition into plus, minus, and wedge parts, here there is only a double decomposition. There is a classical part of each Riemann surface and a quantum part. Again, there's a formal definition in terms of the combinatorics, which is here on the transparency. The details perhaps don't matter that much, but in the end, you end up with this particular decomposition, that a typical surface that contributes to the string perturbation theory expansion after the Keldysh rotation can be viewed as being composed out of the classical kind of backbone part, classical reduction, and quantum embellishments here indicated in green. They are essentially quantum effects. We also have shown that if you take a semi-classical limit of the analysis, this nicely ties together with how we think of conventional classical limits in string theory. The strict classical limit of this picture actually reduces all the quantum embellishments to be trivial, and moreover, reduces the classical part of the diagrams that contribute non-zero values to just a sum over spheres. So spherical topologies, that's the hallmark of a classical string theory approximation. So the notion of classical in the Keldysh-Schwinger sense and classical in the sense of string theory, they nicely and maybe surprisingly, but pleasingly match each other in this particular case. So again, I would speculate that it should be possible to relax the fact that the topologies of all the surfaces is measured by contributions, which are powers of 1 over n. There should be a possibility of having a classical versus a quantum version of the string coupling. But since I'm out of time, I think I'll just jump to conclusions here and say that the topological analysis of the large n expansion of known non-equilibrium features in a matrix system, such as QCD or n equals 4 super Yang-Mills, or just a matrix model, reveals a surprisingly rich substructure expected from the dual string theory description of the same system. And it is this substructure, especially in the case of the original plus-minus description, which is the plus-minus forward-backward prescription is in some sense more fundamental than the Keldysh rotated version. In this case, the triple decomposition of surfaces into sigma plus, sigma minus, and sigma wedge should be really what you're looking for when you're trying to reconstruct the string theory from first principles on the worldsheet side. So the worldsheet theory should somehow be smart enough to know about this decomposition and provide dynamics for all three different parts of this surface. So this is currently work in progress, and again, should be tested by a possible list of interesting examples. So there's plenty of work available for anyone who wants to jump in and look into this more deeply. Our hope, of course, is that this will end up producing some refined worldsheet calculus that will make it possible to make more important predictions for applications of string theory to non-equilibrium systems. But whether or not that will be possible depends on whether we can find worldsheet realizations of these topological features that I've shown you today. So that's it. Thank you for your attention. Happy to answer questions.
Thank you. Time for questions.
Can I ask some, I don't know, basic question?
Sure.
Elementary, I would say. Suppose you're interested in physics of the finite time, in a sense that T wedge minus T0 is a finite, or you have only finite time between, which I think you are interested. And then how do you deal with the fact that if the worldsheet theory is invariant under gauge diff cross wire, as in that usual string theory, any operator you insert is getting some kind of like on-shell condition for the dispersion relation from space-time point of view. I thought that's kind of strongest limitation of the string theory, not necessarily just a time-fold issue.
Now, the question is whether that is the full story or whether that's only a half of the story, whether there is a refinement that allows for more subtle correlations between the plus and minus sides. Maybe, so for example, when you take the equilibrium zero temperature limit, what you expect these plus minus propagators to become is just simply the on-shell condition. So in that limit, this essentially matches with what we know is calculable in string theory. Of course, the main obstacle against doing what you were suggesting, namely keeping the distance between T0 and T wedge finite, we don't know how to do that in string theory in principle in the worldsheet picture, because we have no possibility of cutting out half of the space-time and imposing some brute force boundary condition, unless you do it in some sophisticated orbifold way or something. In other words, what I'm saying is all the target space-time coordinates x mu, they fluctuate logarithmically. They have logarithmic infrared divergences on the worldsheet. So in some sense, the string automatically quantum mechanically fills the entire space-time, and it's not up to you to be able to localize the string in some finite slab between some initial and some final state. That's why formulating the initial and final boundary conditions problem would be so difficult in conventional string perturbation theory. But what we are hoping here is that the signs that we are finding in the triple decomposition of the surfaces points in a direction where perhaps there is going to be maybe a slightly weaker set of relaxed boundary conditions. It's not going to be necessarily possible to formulate the evolution between some initial and finite final fixed time. But there is a way in which the two regions plus and minus can communicate, at least through some on-shell vertex operators, essentially.
Yeah.
But again, this is pure speculation.
It's all speculation, but is it feasible to even speculate that the issue is related with this gray thing we talk, like black and white, like a double scaling limit? Because if you have a gray thing, and you have to probably, and then if you have a gradient, locally, I don't expect that there is a wide transformation, because if you blow up, then probably like a changing rate would change, right? So this is kind of spontaneously broken, or the even locally the diff invariance or something like that.
It could end up being that in interesting examples like critical superstrings, let's say, perhaps the structure is completely non-local between the two sides of the worldsheet. So there would be essentially a double scaling limit required in order to make sense of how it connects to conventional strings. I'm agnostic on that. I'm still trying to look for simple examples which would have this on-the-nose triple decomposition into finite numbers of handles in all three parts of the decomposition, instead of having some large number of wormholes connecting the two sides, for example.
But can you like think about some like this grayness by some single numbers throughout continuous function of the worldsheet or something, and motivated by your thing? But it's you're now doing step function, right? Okay.
Yeah,
Three step.
We haven't really spent much time thinking about what would correspond to the double scaling limit, where you have to allow for this grayness or non-locality between the two original parts of the worksheet. So the question is whether we can find simple examples where it doesn't have to go that way, where we can find the local dynamics individually for sigma plus, sigma minus, and sigma wedge, and by connecting them by a rational set of rules, you would reproduce conventional rules of unitarity, for example, in scattering amplitudes. And I think that should be possible, at least close enough to equilibrium. We should be able to, for example, prove perturbative unitarity using this method. And that's something that's surprisingly out of reach of conventional covariant string perturbation theory, just proving unitarity of string amplitudes. The only way how you can prove it, well, there are two ways. You can either prove the picture by light cone string like Stanley Mandelstam famously proved that the Hughes matrix is unitary. Then you can prove that covariant perturbation theory is unitary by being equivalent to light cone. That's not a satisfactory picture.
Yeah, and that's disastrous. That's disastrous to show that. Yeah.
That's still the best we can do.
Yeah.
Unless we invoke some formal arguments from string field theory, which they have their own drawbacks.
Yeah.
So the first challenge would be, can we use this triple decomposition that's showing up to improve our understanding of unitarity of equilibrium amplitudes? And that should be within reach, because the formalism should be smart enough to have that built in. It's just that we haven't looked at it from the right perspective, perhaps, until now that we see what kind of topological ingredients are playing a role. We are being educated on what questions to ask, and we can try and see if the answers are ready in conventional language of conformal field theory in the worldsheet.
Okay, thanks.
So should I think on sigma wedge, its signature is Euclidean, and the sigma plus and minus are Lorentzian?
It's one of the possible speculations that you can say, I'm trying to connect two Minkowski signature worksheets, and then what is the natural geometry that I'm expecting from the wedge region. You can also think of it in a different way as being a region where the metric of the original worldsheet formulation is degenerate in some sense. So it could be that this is related to some tensionless limit of string theory instead of picking a particular signature. But it looks to us that the picture that's emerging from here is not just a simple possibility of having 2 or 3 branches of a time contour. Instead, what's being analytically continued is really all the field configurations. You should be able to see even much more complicated configurations where portions of the worldsheet are in Minkowski signature, portions are in Euclidean signature, and you're essentially following a very complicated contour in a complexified space of these fields. That seems to be the more appropriate language for what's showing up. But yeah, this is one possible speculation you can have, that perhaps the dynamics on the sigma wedge region should be filled in using a Euclidean signature path integral. Whether or not that's the correct answer and for what kind of initial states, that remains to be seen.
So in general, it's even though you started with the 2 wedges, the corresponding string perturbation theory is kind of very mixed.
Yeah, it certainly carries more information, which should be, of course, logically there, because if we are able to somehow relax the information about the initial state from being just a naive Minkowski vacuum to being a more complicated state, then the information about that state needs to be encoded somewhere. So it looks to me that a lot of that information is encoded in the intricacies of that sigma wedge region, and in particular the string coupling in the sigma wedge region should be perhaps 0 in the equilibrium limit, but maybe non-zero as you take away from equilibrium, and and that carries some independent information about the state
Mhm.
you started with. Not just
Oh, so that makes me. What kind of action are you taking in the third?
well, the beauty of this large N argument is that it's a beauty and a drawback, of course. This makes no predictions about worldsheet actions. This is purely derived from the topology of the large N expansion. So it gives you zero information about how the local dynamics on the worldsheet can be formulated or whether it is even local. It gives you some hints. For example, you can show that even though the topology of the wedge region can be arbitrarily complicated, if I map this to the usual idea that in matrix models, the number of plaquettes measures the area of the surface, even though the topology of sigma wedge is arbitrarily complicated in the number of handles, the geometry is always effectively one-dimensional. You can show that by studying the Poincare dual graphs of the diagrams in the sigma wedge region. In some sense, these are really geometrically, again, only graphs which are effectively one-dimensional, even though they carry a non-trivial two-dimensional topology. So that gives some hints about the dynamics, that the dynamics should be in some sense more degenerate than on standard equilibrium worldsheets. But we have no prejudice one way or another what kind of action, if there is even a local action, we simply don't know. Just like, this is like in the years following 't Hooft's original proposal, to a large extent, this is still true today for QCD itself, right? We still don't know what is the best way of thinking about the possibility of local worldsheet dynamics for the QCD string. There have been various more or less educated proposals, but nothing complete. So this is very similar to that story. So we need some additional input. Like in the case of supersymmetric CFTs, you have large N versus string theory duality, which is very well under control because of supersymmetry. So perhaps here we need some additional insights from additional symmetries to propose some examples which work well away from equilibrium. But a priori, we have no action that we would be putting in on the string side. That's a complete mystery. Step by step, I guess.
Yeah. Of course, that makes sense.
More questions? If not, let us thank Petr again.